All right, so the circuit that I give you there is a very similar, like in problem one, the circuit I give you is basically just like what you would see if you had a tree falling on a power line in the middle of a storm. All right, I like that example because it's the kind of thing that I think about a lot. The only thing that's different is if I had a power line would basically be a inductor and a resistor, right? And I've got a load, 100 ohm load. Now, in this example, I put a capacitor in there. Okay. Now, when you go through this problem, the one that I'm going to do here and the one that you have in problem one, we're saying we close this switch at t equal to 0. All right, and again, looking at the actual problem that's in the assignment, there's no switch. Basically what I'm saying is like if a tree falls, you get a short circuit, right? So the load's no longer getting any voltage, all right, but there's a short circuit there, right? So fundamentally, if I put a short circuit in that problem, what should happen to the current coming out of that source? After t equal to 0, is the current going to be bigger or smaller? Bigger. Better be bigger, right? Why? So first of all, I talk about in this problem impedance. You guys know what impedance is, right? Who doesn't know what impedance is? Everybody not know what impedance is? All right, somebody's brave enough to raise their hand. I appreciate the bravery there. So you guys, let me put, maybe a better question is, have you guys talked about impedance in 2112? Maybe you don't know what it is yet. Start my recording again here. So the problem here, basically, this is just like problem one. So I want to find the amplitude of the steady state capacitor voltage once the switch closes. All right, use impedance analysis to determine the amplitude of this current. So in other words, what I'm asking for here is for, oh man, I'm really in trouble. T greater than or equal to 0. I think this guy might need a new tip. Okay, T greater than or equal to 0. All right, I'm not concerned about anything before t equals 0. Same is true for the problem on the assignment. Okay, so I got to write a differential equation that allows me to solve for all this stuff. Okay, all right. So I wasn't going to start there. I was going to jump down a little bit, but let's start with this. All right. So find the amplitude of the steady state capacitor voltage once the switch closes. So let's say I wanted to do that. And I want to use this impedance analysis. So once the switch closes, how does the circuit change? Yeah, so does R2 matter at that point? No, right? I got a short in parallel with that, so he's gone. Okay, so if that capacitor was a resistor, right? So just to make sure you guys follow, what I always do is I say, well, if I go into a situation where I'm using impedance, then I redraw this circuit in the impedance domain. Okay, which is to say that the voltage here gets replaced by its phasor. Right? What's the static phasor that goes with this guy? For e to the negative j phi. All right, that basically the voltage source is no longer just 5 volts or whatever. It's got a magnitude of 4 volts and it's got an angle of whatever that phi is. Okay. And then there's the capacitor. That gets replaced by an impedance, Z sub C. And the resistor here, R1, gets replaced by an impedance. But in this case, it's just R1, doesn't change. Ugh. Like that. I don't know what's going on. Okay. All right. So what is Z sub C in this case?
Negative 15.9 is what I got.
All right, you skipped ahead on me a couple steps here. So how did you calculate that?
I said -1 over 20 pi times 0.001. Obviously, that's multiplied by j. But
Okay, so 1 over, yeah, what you did is you said 1 over j omega c, right? Where omega in this case is 2 pi 10. 2 pi 10, right? And then c is 0.001 farads. All right, so you calculate that. And what did you say that comes out to?
that came out to -15.9 j.
Yeah. Okay. So what that says is the impedance has a magnitude of 15.9 and an angle of what? -90 because of the negative j. Okay. Negative j would point down. Okay. Negative signs are always angle. Negative signs have nothing to do with magnitude, right? So this guy's got a negative angle. All right. So it tells me about the phase shift there. So in other words, when I'm going to treat that Z sub C like it's a resistor that has a complex value. Okay. So if I said I wanted to figure out the voltage, how do I solve that? I solve for the phasor of V sub C. Okay. So V sub C is the voltage here, across there. Okay. How do I solve for V sub C?
Ohm's law.
Ohm's law. Okay, but in this case, what kind of circuit do I have? They're in series. So I have a name for that I like to use.
Voltage divider.
Voltage divider. All right, if I got a voltage divider, all right, V sub C equals 4e to the negative j phi times what? So I'm trying to find the voltage across the capacitor. So what goes on top and what goes on bottom?
The impedance
Yep.
of the capacitor over the impedance of the capacitor plus the resistor.
Yep. Like that. All right. I go through that whole process like that. Okay. And from that point onward, so this becomes, if I look at this, what am I asking you for? Let's look at my question. Find the amplitude of the steady state capacitor voltage once the switch closes. Okay. Find the amplitude of it once the switch closes. So if I'm asking about the amplitude, I don't care about the angle part here, do I? Right. So what I'm saying is, okay, let's solve for the amplitude. Okay. So then I take the magnitude of both sides of that expression. Okay. So when I have the magnitudes of complex numbers here, like I do, I can say, can I say this? So this is the magnitude of 4e to the negative j phi times the magnitude of Z sub C. I'll write it this way. Everybody follow that? Right? So a magnitude of A times B over C. Right? So that's the magnitude of A times the magnitude of B divided by the magnitude of C. Okay. So if I start plugging in stuff here, what's the magnitude of 4e to the negative j phi? 4. Okay. What's the magnitude of Z sub C? So you just told us, right? Negative 15.9 j. What's the magnitude of that? Not negative, right? What's negative? Negative is an angle, right? If I have a negative, so what's the angle of -1? 180 degrees, right? The angle of -1 be 180 degrees. So what I have here, the magnitude is 15.9. The fact that this is negative 15.9 j means that if I put this guy in complex form, it would be, or in angle form, this would be 15.9 with an angle at -90. All right, that always confuses people, the negative sign. Okay. What do I have on the bottom? Well, on the bottom, I have my R is 1,000 minus what? Minus J times 15.
J.
Yep. Right. So, and that's a magnitude. So this becomes 4 times 15.9 divided by the square root of 15.9 squared plus 1,000 squared. Okay, plus, man, can't do it. I don't know what's going on with my screen here. All right. All right. Imagine 1,000 squared written there. It's not letting me write down there for some reason today. But you guys should see the approach. In fact, let me just, all right, don't want me to erase down there either. All right. So if I had to calculate that for me, what I would do is I would go to MATLAB and I would say that I have, all right, I would have 4 times absolute value negative j times 15.9 divided by absolute value of negative j times 15.9 plus 1,000. Right? I'd put it in there like that. I don't know what that sound was. All right, so 0.0636 is what I end up with. Okay, so if I go back to my PowerPoint here, all right, this guy is 0.0636. All right, once I get through that, and maybe I can write. Okay, whatever. Still can't write on it. All right, 0.0636. What is that again? That, yeah, so it's the magnitude of the phasor, it's the amplitude of whatever that sort of cosine is going to be on that thing. Okay, so I was just saying that's a lot faster. You should, once you get comfortable with it, you can see that's a lot faster than writing differential equations and going through that whole process. Okay, so need to go through that difficulty if we don't have to. All right, the next part, it says write a differential equation that allows you to solve for VC of t after t equals 0. Okay, so after t equals 0, we already said this guy is shorted now. Okay, so how do I want to change my marker here to change my color, red. Okay, so he's shorted. Okay, how do I write the differential equation now to get to v sub c? What would I have to do?
Use KVL.
Use KVL, right? And without going through the details here, if I'm going to call this guy v sub s. All right, I'm going to get that v sub s equals R1c dvc dt plus v sub c. That's what it's going to end up being. All right. I don't want to go through the analysis on that, but you should see that that is correct. All right, if you went through it. All right, this isn't circuits. We've spent enough time already on circuits. All right, so that's my differential equation. All right, now the problem, if I look at the rest of this, that's all you got to do for part B. Part C is this. Okay, think carefully about this. And I wasn't paying attention to it last night. I saw somebody at 10 o'clock last night was think carefully about the steady state and transient solution to your differential equation to determine an appropriate time step that allows you to see both the transient and the steady state. Explain your choice. Okay, that basically gets into what we started talking about previously. Okay, so we've talked about this before. So how do we, so let's, before I jump ahead to anything about the time step, without solving this, I'm not asking you to solve this differential equation by hand. You can, all right, as a check on yourself. What does the solution to this differential equation look like? What does v sub c look like? What is it? What is the total solution? Yep. B cosine omega, and omega in this case is 2 pi 10. Okay. Plus, I'll call it theta to have a different angle. All right. And what else is there? So right up here. What else is in this solution?
Plus CE to the negative T over tau.
Yeah, CE to the negative T over tau. All right, and I don't want to call it C because I got a capacitor, I guess. I'll call it A. All right, so I got that expression. So that's what it is, right? What do we? So when we look at that, what do we not know? We don't know B. We don't know theta. We don't know A. We don't know. Do I know tau? You guys should know. This is an RC circuit. Do I know tau? Yeah. What's tau here? RC. All right, and specifically R1C. So if I did that, that would be equal to 1, I think. Right, 0.001 times 1,000 should be 10 to the minus 3 times 10 to the 3, or 1. Okay, so so what I don't know is A, what I don't know is B, and what I don't know is theta. Okay, now it's a differential equation. I need to know some other stuff too, right? Don't I? I need initial condition, don't I? Yes, there are two things that I basically haven't told you in this problem. All right. And I'm asking you, if you look back at this, all right, you should be able to figure out later on, you should be able to figure out what the value before t equals 0 is. All right. I'm not doing that right here. What I'm asking you to do, actually in part C, this one, I'm not concerned at all about what the initial condition is at this point. All right, we will be later. All right, I don't need to know anything about that to say, all right, I want to be able to see the transient and I want to be able to see the steady state. So when I talked about this before, all right, so how do I think about this problem? I got two choices, right? Choice 1 and choice 2. All right, what were my two choices?
You can either use the frequency or use tau to determine your time step.
Yeah, well, so in this case, I either, yeah, so I use the transient. And then I use the steady state. And I figure out which one requires which one requires the smaller or bigger time step, which one controls it. The smaller, okay? So to see the full transient, what did I say we needed to do? How long does the transient take? 5 tau. Okay, so I said, all right, the transient takes 5 tau. So I want my delta t, my time step, to be much, much less than 5 tau. All right. So what was our definition of much, much less than? 100 times smaller, so 1% of. So in other words, delta t should be less than 5 tau divided by 100. Okay, so that means that delta t for this choice, if RC, the tau here was 1, so I've got 5 divided by 100, so that's what, 0.05 seconds. The delta t needs to be smaller than 0.05 seconds. Okay. What about for the steady state? What do I use there? Well, so yeah, what is the period? 2 pi 10 is our frequency, omega. So what's our period there? What's our period? Man, I can't use the bottom. All right. We'll go over here. Choice 2. All right, the steady state. So our period is what? 1 over 10, right? So 2. So I have 2 pi times f. F is 10. So 1 over 10 or 0.1 seconds. Okay. So in this case, for this second choice, I want to see a full period of that thing. What did I say? How did I choose my delta t for this guy? Much, much smaller than what? T, yeah, much, much less than t, right? I need the period to be, or I need the time step, delta t, to be much, much smaller than a period. All right, so what was our definition of much, much smaller then? Okay, yeah, at least 100 times smaller, like that. Okay, so in this case, I would say, well, delta t needs to be smaller than 0.1 divided by 10 squared So 10 to the minus 1 divided by 10 squared is what? 10 to the negative 3, okay, or 0.001 seconds. All right, so what we sort of said before is I look at both of my choices. So I have a choice that comes from the transient, and I get a choice that comes from the steady state solution. Okay, I look at which one imposes the smaller requirement. That's the one I have to go with. So in this case, choice 2 was I needed to see the steady state. I needed a time step that was less than 0.001 seconds. To see the transient, I needed a period that was less than 0.05. All right, so I got 0.05 and 0.001. Which one should I choose? Well, so which one's the smallest value? 0.001 and 0.05.
0.001.
0.001. All right, this is our guy. All right, that's our choice. So if you go back to the problem I'm asking you here, so part C, think carefully about the steady state and transient solution. This is the process, right? You basically say, well, I know it's going to be A e to the negative t over tau plus B cosine omega t plus an angle. And I got to look at both this. I want to see both the steady state and the transient. So you got to think through carefully, how do I make the choice? All right. That's what we just did. We looked at choice 1 and choice 2. The transient choice number 1, was the door that we chose to open. Okay. All right. So you're basically kind of walking me through that decision process. All right. Now, we're done with that. Any questions there up to that point? All right. You basically, now you got an LR circuit, you don't have an RC circuit. Well, that means your time constant is going to be different. Right. So you've got some different things to worry about, but fundamentally it's the same process. Okay. There's nothing different about what you're doing. Now what do I need to do? Then it says part D here, write a MATLAB script that solves for the voltage V sub C of T after T equal to 0. All right. So at this point, we got to write a script to do that. Okay. To approach this problem, assume that V sub C of 0 equals 0. Because what? I need an initial condition. V sub C of 0 equal to 0. That's what I said. Now, I also say try several different values of phi between 0 and 180 degrees. For what approximate value of phi does the value of V sub C of T become the largest after T equal to 0? Okay. So in other words, the value of phi kind of matters. It changes what the initial condition does. All right, so this is the part here that I think kind of screws people up. Is phi is like a variable to you. When you approach this problem, just start out with setting phi equal to 0 and V sub C of 0 equal to 0. All right, that is not necessarily true. What I'm saying is and this is the way I'm thinking about this problem. So here's why it even matters. If a tree falls on a line, this is the problem I'm trying to look at. Tree falls. I don't know where the voltage is going to be when the tree falls. In other words, Mother Nature doesn't control, fall when the voltage is 0, right? It just falls wherever it is. Okay. And the way for me to be able to model that is to change this angle. All right, because T equals to 0, this guy is always 0. So I just play with the angle of phi to say, well, how much do I want it to be offset from where it should be at 0 by playing with that angle? All right, so you can do your analysis assuming V sub C of 0 is 0 and phi is equal to 0. What I ask you to do later in the problem here is part of this problem is I'm asking you to find the value of phi at which V sub C of T becomes the largest after T equal to 0. So my suggestion is once you get the code to work, right, what I would do is I would try phi equals 0 and then try 45 degrees and then 90 degrees and 135 degrees and 180 degrees. And trying that's trivial, right? Because you've written code, you just change one variable in the code. Well, try it at 0, try it at 45, try it at 90. Right? And you're going to see what happens. If you've done it, you'll see the transient changes a lot. Steady state doesn't change, but the transient changes all over the place. All right. And in the context of power systems, that's a problem because I end up getting kind of beyond the scope of this class, but it changes the way a circuit breaker behaves. All right. And so we need to worry about worst case conditions usually. All right. For you to approach this problem at this point in part D, V sub C of 0 is equal to 0. I think in the problem, it's the current is equal to 0, T equal to 0. And assume phi is equal to 0. Once it works, once the code's working, then start changing phi. All right. So there's really two steps that I'm asking you to do right there. All right. I'm asking you to get the differential equation solver stuff done. And then I'm asking you to start playing with the angle phi. All right. And that changes what the transient response looks like. All right. So how do I write the code here? How do I begin with the code? All right, so I had V sub S, this guy, equals R, well, I'll write it this way, tau dVc dt plus Vc, like that, right? What's the step that I take here? So I'm doing this, I need to discretize that equation. How do I do that? What's the key step to discretize this thing?
Plug in the expression for the derivatives.
Yeah, plug in the expression for the derivative, right? So we have the dVc dt is the limit, right? Limit as delta t goes to 0 of V sub c of t plus delta t minus V sub c of t all over delta t, like that. And we said, all right, well, if my delta t is small enough, that's the whole point. My delta t is small enough, what do I do with the limit? Get rid of it. And just say that's approximately equal to each other. And I drop that into this expression. So I end up with tau V sub c of t plus delta t minus V sub c of t all over delta t plus V sub c of t. And that's equal to Vs of t. And I got to be careful to put in the of t. All right, so when I have this expression here, so this is what I've done is I've quote unquote discretized this thing. I'm not solving at every value of time. In other words, I'm not solving at every real number t. I'm solving at so in this case, what have we chosen as our delta t? What did we choose? I think we chose 0.001 seconds is what we chose. So what times am I solving for the voltage? I'm saying I'm solving for V sub c at 0, and then at 0.001, and then at 0.002, and so on and so forth, right? So I'm not solving at all the values. I'm solving it at delta t, 2 delta t, 3 delta t, 4 delta t, 5 delta t, so on and so forth, right? I'm solving at all of those different points. So what I ended up saying is, what does this mean? This is the value right now. This is the value right now. This is the value right now. What is V sub c of t plus delta t? It's the value in the future, one step ahead, right? The value right now can predict for me the value one step ahead. So I basically ended up writing this and said, well, I could also say this is V sub c of n, the current value. All right, so tau over delta t, and then this becomes V sub c of n plus 1 minus V sub c of n plus V sub c of n. All right, so way I wrote this is I have an algebraic expression here. I know what this is. V sub s is this guy. All right, so I just keep plugging in t values, and I can solve for what V sub c of Vs of n is. Okay. At time t equal to 0, I know the capacitor voltage. I know the voltage of the source, so I can solve for the value one step ahead. Right, so I end up with an expression. I don't want to go through all the math on it because I'll probably end up screwing it up, but here it is, right? V sub c of n plus 1 equals x, so v sub s of n minus v sub c of n plus a times v sub c of n. This is in the notes from before too, all divided by a. All right. And my a value, I have it defined here in the code, is my a was tau divided by delta t. All right, where did that come from? Well, that came from doing the algebra on this thing to solve for v sub c of n. Right. In other words, v sub c of n plus 1 is equal to v sub s of n minus v sub c of n plus a times v sub c of n, all divided by a.
Can I ask a quick question?
Yeah.
If we put the differential equation in standard form before we discretize it, would that cause any issues?
So what is standard form?
The coefficient before the derivative is 1.
1. Yeah. Okay. Yeah. So he's asking a great question, because some of you guys are going to screw this up. Yeah. I'm glad you asked that question. If you go into my formula, if you go into my notes and you use my formula, like this formula right here was derived assuming it was this form. If you have a differential equation that looked like this, I guess, then this relationship here is not valid. Okay. You would have to rewrite that. So in other words, all the math that I just did here, I plugged this definition into this expression, and then I solved. Great question, Anthony. Yeah, if you don't have it in that form, my result here will not work. But if you have it in a different form, the same process works. All you got to do is plug this in, and then do the algebra like I'm doing. All right, which you should be able to figure out. It's just algebra. If you understand that how I got to this answer was that I made this substitution and then did algebra to solve, then it's trivial. But if you start out with a differential equation in a different form, you'd have to start from scratch on that process. And that's probably important for you, because you may end up with a differential equation that does not have that form. And I wouldn't be surprised if potentially in this problem, it's not in that form, in problem 1 or problem 2. All right, but it's pretty trivial to get it switched over. Does that answer your question, Anthony?
Yes, thank you.
Okay. All right. So yeah, be mindful of that. All right, because I know probably a lot of people will screw that up on the project, is they won't pay attention to that. And that's a big hit. That's a big hitter. If you just went to my notes and pulled an equation out of my notes and didn't think about it and ended up with the wrong answer for an assignment you had for 2.5 weeks, I'll hit you hard on that. Okay. All right. I'm expecting that you notice that difference. All right. Okay. All right. So at this point, I'm ready to write the code. And what I said was start out with a phi value equal to something. So I started out with phi equal to 0. Now, notice I've put a number in here. All right. Well, what I'm telling you for your initial condition is start out with it equal to 0. All right. When you do that part, set it equal to 0. Here is where I'm solving the differential equation, this for loop, right? So the for loop, I have this, what's this if statement here? What's this if statement I've created? It's to check the initial condition. So in other words, I set up a time vector. In this case, I set up a time vector that runs from 0 in steps of delta t up to 6 times tau. Where do you think the 6 times tau came from? Why 6 times tau? Yeah, so I can see the full transient, right? Maybe I could have said 5 tau. I know that if I went to 6, I definitely see it all. All right. So I did that. And then basically I created, so X here is my input. All right. And then V sub C, I don't have to do this, but I did it. I made V sub C a vector of zeros. All right, so zeros with the same size as t, and then I solve for b sub c. All right, now let's run that code. So here's, all right, here's the expression. Let's start out with, now remember, when you're in the regular MATLAB tool, all right, my suggestion to you is to have the clear all, right? When you're in the Canvas MATLAB in the browser, clear all kind of screws everything up. But here you need it. Trust me, I see a lot of people on project stuff screw up because they don't have the clear all. Because if you had a variable defined and then you run another set of commands, it's going to use whatever you had defined. All right, which may crash your computer. All right, I've seen that happen. All right. All right, so I start out with these values, and I run it and look at it. And I get that. Okay. Now, if I look at this, the reason why did I tell you to get the amplitude in part A? Because I wanted you to be able to feel comfortable that this is correct. All right. So how can I tell if this is correct? If I look at the amplitude of this, right? If I look at the amplitude of this, what is the amplitude here? If I put my little data tip on, all right, this guy looks like he's peaking around 0.063 something. And if I go back to whatever we calculated, it was what? We calculated, here it is, 0.0636, all right? So what we're seeing there in MATLAB looks pretty darn close to what we expected it to be, all right? So I feel pretty comfortable that I've got the right answer at this point. Now you can solve the differential equation by hand if you wanted to as well, all right? If you're a person that wants to get an A, you probably will end up doing that anyway. All right, but for me, what I got for part A and looking at this makes me feel comfortable that that my code is working. Okay. Now the second part of part C here was, or part D, I guess, is try several different values of phi between 0 and 180 degrees. For what approximate value of phi does the value of V sub C of t become the largest after t equal to 0? So my suggestion was try values 0, 45, 90. So let's try it. Okay, let's go back to my script. So I did that for phi equal to 0. So what happens when I choose phi equal to 45 degrees? I gotta be careful. What do I do? Okay, so I notice in my code I put 45, and then I have a conversion there. All right, so let's try this. Now, all right, now it changed. What happened? Has the steady state changed at all? No, steady state doesn't change, right? But the fact that phi was different did what? It changed the transient, right? What do I notice about the transient now? Well, it's a lot clearer to me, right? So if I look at this, basically the voltage is jumping up above 0, right? That's the effect of the transient response. That change in that value of phi basically lifts this guy up off of 0 for a while. All right. This problem, like I said, this problem is a common problem in circuit protection, because if the tree falls at the wrong time, then the voltage that should be an AC voltage is way above 0 for a while. Right. That's the nature of this problem. For a power system person, that's a big problem. All right. So if I keep trying phi, what do I notice? Well, I tried 45 degrees, and let's take a look at it. 45 degrees, the peak value there is a little bit more than 0.1. Okay. Now let's try making it 90 degrees and see what happens. All right, 90 degrees, and run it. All right, wants me to save it. Let me not run it. Execute. All right. Oh, now it's even higher. All right. So it was a little bit more than 0.1. Now it's getting, it's almost up to 0.15. So let me try now 135 degrees. 1, 3, 5. And let's run that. So now I'd have to check, but it looks like it's maybe a little bit higher than it was before. And then I can try 180 degrees. And I don't want to do run. Execute that. Oh, it looks like it's back to where it was before, right? So if you go through that process, what you actually see is that in this particular case, if I look at it at, let's see, 90 again. And if you wanted to, you could, if you're clever, you could write a little for loop. You could come up with something if you're a clever little computer person, right? So I can look at this guy's 0.122. If I tried 135, I'd actually see it's a little bit lower, I think. Yeah. So it's actually a little bit lower, 135, right? 0.105. So where did it max out? 90 degrees, right? I don't know what it does in the problem that you have, right? But it's the same sort of thing. At what point does it kind of max out? If I were to keep going and I were to go past 180, what I'd see is instead of it going above 0, it would go below 0, right? And some of you guys may have already done that. All right. So that's the basic process for that. Okay. So what's the rest of that problem asking? So the rest of the problem is, okay, using your value of phi from part D. So we just got that phi here was 90 degrees. Phi equals 90 degrees. Use impedance phasor analysis to determine a function for the voltage V sub C of t right before t equals to 0. Use this expression to find the true numeric value for V sub C of 0. All right, what am I asking there? Using the value of phi from part D, use impedance phasor analysis to determine a function for the voltage V sub C of t right before t equal to 0. What the hell am I asking you to do? Mhm. That's right. Yep, because I'm using the static phasor. I can go in. So basically now what I'm saying is what's the circuit here? So I'm asking you before t equal to 0, what's the circuit look like before t equal to 0?
It includes the load resistance.
It includes the load resistor. Is it still a voltage divider? Yes. Okay. So what I do is I change this expression now. I make this a 90 degrees. Okay. Phi was a 90 degrees. Okay. And I did have the minus sign in there, so it's minus 90. So I replace this guy with, so my way of thinking about this is I redraw the circuit and I have 4. And if you don't want to, sometimes the E to the J or whatever confuses people. When I'm in 2112, when I teach that, I don't use it. I just say, well, you'll feel more comfortable if I make it negative 90 degrees. So it's 4 with an angle of negative 90. Okay. That's equal to, what do I do? What am I, well, I'm not trying to, I just want to redraw the circuit first. So what do I replace the capacitor with? Not an open circuit. So I'm doing steady state analysis. I'm doing impedance stuff now. So I just replace it with Z sub C. And I replace R1 with R1 and R2 with R2. R2, R1, and I got it. Now, Z sub C is what? Z sub C is 1 over J omega C. All right. What do? I plug in omega and I plug in C. What was omega again? 2 pi 10, right? So we put in 1 over J, 2 pi 10 times 0.001, which somebody told us was negative J 15.9. All right. So so I don't want to, I don't like doing it that way. What I prefer to do, I don't like numbers. I like equations because I can see equations. I can make sense of equations. I can't make sense of numbers, right? Whether the impedance of a capacitor that's 0.001 farads has a value of 15.9 or 159, it's hard for me to say, right? What makes a lot more sense to me is when I look at this expression, I can make sense of it dimensionally if I write it out. So if I want to figure out V sub C, the static phasor for that voltage, how do I get that expression from this circuit? How do I get the static phasor for V sub C? Well, yeah, so IC times Z sub C would be the, yes, certainly. But this guy's a voltage divider, right? We don't know what IC is, right? So if I wanted to solve, so think about, so what I say is once you're in the phasor domain, think of them all as resistors. No. All right, how do I get V sub C if I think of those three components there as resistors?
Add them all up in series.
Yep, and they're a voltage divider, right? So I have Z sub C over what? But don't tell me you remember the voltage formula as R1 over R1 plus R2, right? The voltage divider formula is the resistor you want divided by all of them, right? So what do I have on the bottom? Let's forget about it. Let's assume I don't know anything about anything, right? So if I wanted to find the voltage across a single component in a series circuit, and I know the voltage going in, and I got a bunch of resistors in parallel, how do I figure out the current? What's the current in that series combination of stuff? What's the current in that series combination? It's the same. So how would I find it based on what I have here? Okay, what's the equivalent resistance here? Z sub C plus R1 plus R2, right? So I'd say the current is, so I would be 4 angle negative 90 degrees divided by Z sub C plus R1 plus R2. That's the current. Now, how do I figure out the voltage on the capacitor? I times Z sub C. So that becomes 4 angle negative 90 degrees times Z sub C divided by Z sub C. Crap, I'm too low again. There we go. Z sub C. This is really annoying. V sub C is equal to 4 angle negative 90 degrees Z sub C over Z sub C plus R1 plus R2. Right? What I did was I solved for the current, then multiplied by the impedance to get what the voltage is. All right. That should be something that you're familiar with. Okay. So, all right, I'm going to get V sub C. So what am I going to get when I do this? What result am I going to get? Well, V sub C is going to be a complex number. It's going to have a magnitude and it's going to have an angle. I don't want to solve for them. Let's say I did, and let's say I got 8 with an angle of negative 110 degrees. I have no idea if that's the answer. Let's pretend that it is. All right. If that's the case, if that's what I get, so I'm writing this in polar form because I think you guys like that better. That's the same as e to the negative j 110. All right. What I ask for is what's the expression for that voltage? So what's the exact wording I used? The exact wording is, yeah, determine a function for the voltage V sub C of t. Okay. So what is the function for the voltage V sub C of t here? If this is the static phasor I solve for, what is V sub C of t? Mm-hmm. Yeah, what's my cosine? What's my omega? 2 pi 10 t minus 110 degrees. It's messy to use the time domain. Using phasors is a lot simpler Because the only things that can happen in steady state is you can change amplitudes and you can change angles. Phasors track those two things for you and get rid of the time. The time doesn't change anything. Now, what I say is this gives me the real initial condition, because I can go in and I can say, well, plug in V sub C of 0, and that becomes 8 cosine negative 110 degrees. Okay. So I do know, for whatever reason, I know that phi is 110 degrees. All right, if I solve it. Once I have that, all I got to do is go into my code and put in my values. Okay, that's what I did. I just changed my code to the right value, and phi was something that we already chose as 90 degrees. That's all I got to do at that point. All right, and I'm done. I think that was the last part of the question. I think. Yeah, rerun your script. All right, what's the peak voltage now? Right, so I'm basically just asking you to rerun it in the last part. Okay, so if you know what you're doing, this thing doesn't take you too long to do it. And then problem 2 is very similar to that. All right, problem 3 is where it starts to get harder. What's the difference with problem 3? Well, in problem 3, it's second order, right? So you got to go back and look at what we did on Monday. Okay. All right. So that's the challenge with the second order. All right. Questions about that? All right. All right. A little bit of time here. So problem 4, and I saw a comment, went back and looked at it. I think if you look at problem 4, it's referencing a file here, problem3.bin. It's actually problem 4.bin. This problem was problem 3 when I was making it, and I changed it to problem 4. So I'll update the PDF that I have posted. Problem 4.bin, which is posted on the website on the Canvas page, is for problem 4. Problem 5.bin is for problem 5. I will fix this and repost it so you guys, it's clear. Okay. But what you're doing, this is the problem here. This is basically what you're doing is making an AM radio. And I don't mean to imply, AM radio is not necessarily like, you're listening to grumpy sports talk or political talk or whatever, right? So it's actually pretty common. Like your phones are all using AM communications, right? So it's still pretty heavily used. This is what it looks like. So you basically have a received signal. This is the received signal here. There's a really super high frequency signal that you're receiving. So it could be a gigahertz on your cell phone, right? In other words, there is a really high frequency signal. F is high. F is a big number. And you have an audio signal that multiplies it, okay? So what that binary file has is a sampled version of a received signal. So it's basically, if you plot it, you'll see that there's this high frequency wave whose amplitude is kind of going up and down. Modulation means to vary. So it's an amplitude modulated signal has a varying amplitude. If you want to receive the signal, the way you receive it is you multiply those two signals together. You multiply this received signal by something with the same frequency as the quote unquote carrier. That, so if I'm sending something at a gigahertz, I multiply it by something at a gigahertz, follow it by a filter. And the magic of that process, which you talk about more in signals and systems, is basically that Y of t and the original audio are the same. Okay. And you can go through the math on that. It's actually not hard to go through the math if you want to. If you went through the math, you would see that this is correct. Okay. So this is a pretty common sort of process. And what I end up asking you to do here is I have given you a digitized signal here. In other words, it's in a computer, right? So X of t is a analog signal. Analog signal means that time is a real thing. So there's infinitely many samples, but that's not possible in a computer. So I give you a sampled version of that. So one of the commands that you're using here, I tell you to use this downsample command. Because if you don't use that, there's a lot of samples. Okay, so much so this is the kind of thing where you're going to crash your computer. All right, so follow those commands very carefully. All right, we can talk more about that probably next week. At this point, you guys should be jumping into doing work. on the project if you haven't yet. I have my office hours tonight. I haven't decided yet whether I'll really do full lectures next week. I probably won't. We're going to be geared towards project stuff. So this will probably be office hours time of some kind for you guys to ask questions. Okay. No new content again until after spring break. Okay. All right. So I will stop there. If you